Good morning, everyone. I'm Leonardo Soares, and I present a paper entitled "The Fine-Grained Methodology for Accuracy-configurable and Energy-efficient Gaussian Filters Design." This work has been developed by Talita Borges, and she is a master degree candidate in the graduate program in computing from the Federal University of Rio Grande, and she is advised by me and the Cristina Meinhardt. So here's the outline, and after introduction, I will show a proof of concept which supports our proposed approach in configurable solution, and after results, I will show the conclusion. So the semiconductor industry faces challenges. One of them is the high demand for compute-intensive applications such as multimedia, feature extraction, computer vision running on mobiles. And associated with the Internet of Things scenario, we have the high demand for huge volume of data to be processed. And based on these challenges, is mandatory the use of energy-efficient approaches. So the good point here is that most of the recent and emerging compute-intensive applications does not demand high precision all the time. And based on that, emerged the concept that approximation-tolerant application. We can leverage this condition to balance the trade-off between precision or application quality and energy efficiency. So inside the approximate computing scope, we can classify the approaches as being the design time solutions, and here we emphasize the runtime because our solution is inside a configurable solution. So when we talk about runtime configurable solutions, here we have in this graph an example of runtime management, and we can manage the quality of this image processing application according to energy consumption restriction. And then this is a key solution or alternative to manage different power performance and quality profiles during the runtime. Based on that, in this work, our objective and first objective is in design time explore a fine-grained approximation for 2D Gaussian filter accelerators just to observe the energy efficiency. And based on the findings of this proof of concept, we proposed an accuracy-configurable 2D Gaussian filter architecture to be managed during the runtime. We decided to use Gaussian filters in images because this is a prior step in many computer vision and feature extractions applications. This proof of concept in terms of quality is based on a script development by using Python language and OpenCV library, and the approximation is based in the exploration and reduction of the number of bits of both input images and the filter, and this reduction here can be seen as ranging from 7 down to 3 bits. And we use to validate this proof of concept 10 different images from the Berkeley segmentation dataset benchmark. As mentioned before, we adopt the 2D Gaussian filter, and to perform quality assessment, we use the PSNR metric, and the reference is the 8-bit and precise input image, and also the 2D Gaussian filter containing 8 bits. And based on that, every reduction or approximation in the filter and input images after the filtering process, this resultant image is restored in terms of number of bits, or in other words, to 8 bits before PSNR analysis. And then in this graph we can see for the 10 different images under analysis of the benchmark that when we use 5 bits of reduction, we have about 28 dBs. And when we use 1 bit reduction, we have the maximum quality point of 43 dBs. So here we can see that we can explore different points of quality according to number of reduced bits in the filter. So to evaluate the energy response of this proof of concept, we consider here this architecture for the Gaussian filter, and it's implemented with this adder tree and these shift operations, and it is capable to receive as input 25 samples of grayscale image. And here then we can see that this Gaussian filter process 5x5 images, block of images, and per cycle it is capable to output one sample. And then to validate these energy results of the proof of concept, we consider not only the 8-bit version and precise version, but we also consider all bits variation from 7 bits down to 3 bits. Then we have different circuits to be synthesized. And here for 65 nanometers technology node, we can see that the most aggressive approximation with 3 bits, the circuit with 3 bits, have maximum energy reduction of about 68%, while for the 7 bits circuit of the Gaussian filter, we have a minimum energy reduction of about 13.2%. And when we evaluate the area reduction, we also can see the different circuits here, and take in consideration the 8-bit architecture as being the baseline for the same technology. We can see that the most aggressive approximation achieves maximum area reduction of about 60%. So the conclusion of this proof of concept is that it's feasible to explore approximate computing in bit level for 2D Gaussian filter. But the question is how to manage these findings in a runtime configuration. And the answer for that is our configurable and proposed approach in this work. So considering the same architecture we previously shown in the last slides, we here explore inside the input hashers bank, and here we can see it can contain multiple 8-bit hashers, and inside each of these 8-bit hashers we have this structure here, and in this structure the 5 least significant bits has clock gating logic to control with independent enable signals to control different bit reductions and bit switch activities in these flip-flops. Therefore, this structure and our proposed work is intended to be managed by the system or user experience based on different power performance or quality constraints. And of course, if we include logic to control the clock gating, we have additional hardware here. Our experimental setup is structured as follows, and we perform ASIC implementation, VHDL description of the circuit, of the accuracy-configurable circuit, and the tool used to synthesize is the RTL compiler by Cadence, and it is synthesized for the 65 nanometers PDK, and the frequencies of operation are 63 MHz and 249 MHz. Considering real-time operation for these two recent video resolutions running at 30 frames per second. And to do power estimation, we consider real test case simulations by considering different test benches, and each profile, each approximate or precise profile, process 10,000 5x5 image blocks. So this is the experimental setup structure to observe the results. So when we observe the power results here, we have these profiles. So here we have one architecture, and this configurable architecture based on test bands can perform different approximate profiles and the precise one. And here we can conclude that the dynamic power is dominant over the static one. And we also can observe and conclude that the clock gating logic is important to reduce the dynamic power, since it is dominant for this case study. And when we observe the energy per operation response, we can see here that the maximum energy reduction for the most aggressive profile simulated, we can see that this maximum energy reduction is of about 59%. And when we observe the profile with 7 bits, we can see that the minimum energy reduction is of about 9.9%. And this trend for both of the frequencies and technology ratifies the findings from the proof of concept. In terms of area evaluation, here we have the design, the precise design, considering 8 bits and without the configurable logic. And when we consider the accuracy-configurable solution, we have increase in terms of area for both of the frequencies, and this overhead is about 15%. When we compare our proposed work with the related ones, this first work here is a design time exploration with approximate adders, and these two studies here are a runtime configurable, as we do. But our work is bit level, while these other works has a coarser grain. And when we observe our power reductions and compare this power reduction with the other works, we can see that we present similar power reductions, and in some cases we still present better power results than the state of the art. And this shows that we are providing a solution in the direction of the state of the art. As conclusion, we can see that this is a bit level exploration, considering runtime management for approximate computing and 2D Gaussian filter design for image or video processing. And to accomplish energy efficiency, we can then reduce the bit width of the filter to support multiple coil profiles. In terms of the proof of concept, we can see that the energy reduction is ranging from about 13.1% up to 67.8%. And in terms of area, the maximum area reduction is about 60%. And most important here, our proposed approach on configurable architecture, we have an energy reduction of about 9.87% up to about 59%, with an area overhead of about 15% when compared to the 8-bit and precise Gaussian filter. One and more important conclusion here is also that our solution is capable to improve the quality. And this is future work, because we intend to, in the same image, use different approximation given input data content. So this is a direction for future work in this research. I would like to thank you, all of you, for your attention, and I'm ready for questions.